High in the Chilean Andes, beneath some of the darkest skies on Earth, world-leading observatories are reshaping our understanding of the universe, each in their own unique way. This is more than science. It's a search for meaning, a frontier of discovery, and a shared human endeavor worth supporting. Join me as I take you on my journey of discovery in Chile. I traveled to Chile as an ACEAP ambassador and visited some of the top astronomical observatories in the world. I'll share my behind-the-scenes, restricted area access to world-class telescopes, control rooms, operation centers, supercomputers, and much more. But first, let me explain ACEAP. The Astronomy in Chile Educator Ambassador Program is a collaboration between AUI and AURA and the observatories they manage in Chile, including Vera Rubin, Gemini South, ALMA, Soar, and others. It's supported by the National Science Foundation. The program brings amateur astronomers, STEM educators, planetarium and observatory personnel together for an intensive immersion at many of the top astronomy facilities in Chile. When they return home, ambassadors share their experiences and explain the value of the research and the science being performed there. A link to ACEAP is in the notes in the video. As you probably noted already, there are a lot of acronyms I'll be throwing around, so perhaps I should explain them to get you oriented. The National Science Foundation provides funding for terrestrial and space-based optical and radio telescopes. The Association of Universities for Research in Astronomy, or AURA, manages both ground and space-based optical observatories. AURA manages NOIR Lab, which is the National Optical Infrared Research Laboratory. NOIR Lab, in turn, manages many major optical observatories, including Kitt Peak, Cerro Tololo Inter-American Observatory, Vera Rubin, and Gemini North and South. Associated Universities, Inc., or AUI, manages the National Radio Astronomy Observatory and co-manages ALMA. This group focuses on radio telescopes. ALMA, or the Atacama Large Millimeter Submillimeter Array, is the world's highest radio telescope array. More about that later. I arrived in Santiago on Friday, June 27, 2025. After getting settled and having a welcome dinner, the next day we went to the AUI NRAO office for a detailed description of the plans for the next week or so in Chile. At both the front end and the back end of the trip, there were some interesting cultural and nature-related activities, but this video is going to focus on the astronomy aspects of the trip. Let's talk about why put observatories in Chile. First of all, Chile has about 330 clear nights per year, as much as really any other location in the world, good for astronomy. Also, it has very dark skies with very little light pollution. The atmosphere is very steady because of the cold Antarctic current that flows up alongside the country. The air is also very low humidity, which is very important, especially for radio astronomy, but also for visual wavelengths. Chile has low labor and material costs, which helps in the construction of observatories. It also has excellent infrastructure and ease of access. Finally, it has a stable government, which is important if you're making billion-dollar investments. We flew to La Serena on the coast, and our first stop was Alpha El Dia Observatory. This is a business that supports astronomy tourism and is open to anyone. Before sunset, we could see Gemini South and Vera Rubin in the far distance, our first glimpse. We had a nice 3D presentation on astronomy in their theater, and then after a wonderful dinner, did astrophotography under very dark skies. The observatory had a 16-inch Dobsonian telescope, and we looked at many of the Southern Hemisphere's favorite targets: Omega Centauri, Centaurus A, the Jewel Box, Eta Carina, the Running Chicken Nebula, the Magellanic Clouds, and many others. For some in the group, it was their first experience under dark Southern Hemisphere skies, and they were amazed. The next day, we drove to Cerro Pachón, which is the mountain that hosts Vera Rubin, Gemini South, and Soar observatories. Note that from this point on in the trip, Everywhere we went was restricted access. You needed to be invited. The Gemini South Observatory is one of two telescopes that make up the International Gemini Observatory. Located at an altitude of 2715 meters or 8907 feet, Gemini South offers exceptional viewing conditions in the southern hemisphere. Its twin, Gemini North, is located on Mauna Kea in Hawaii, enabling 100% sky coverage. Gemini South has an 8.1 meter diameter mirror made of Pyrex and utilizes cutting-edge technology such as adaptive optics to correct for atmospheric distortion, providing near space-quality images. It supports a wide range of instruments for imaging and spectroscopy in both optical and infrared wavelengths. The observatory plays a crucial role in research on exoplanets, supernova, black holes, galaxy formation, and more. It contributes to rapid follow-up observations of gravitational wave events and other transient phenomena. Gemini is also part of a global collaboration such as the Event Horizon Telescope, which captured the first image of a black hole. We learned that they recoat the mirror every 6 years with silver, which has a better reflectivity than other materials and infrared wavelengths. While there is a control room used by engineering, and we did visit it, Gemini is completely remote controlled. Operators and astronomers are based down in La Serena. Using a plan as a guide, they choose targets based on real-time conditions, such as clouds, the amount of moonlight, and steadiness of the atmosphere. Some targets require different conditions than others. Imagine for a moment looking at a pebble at the bottom of a pool. If there are ripples on the surface, the pebble will appear distorted. The same thing happens when a telescope has to look through our atmosphere. It's why stars appear to twinkle. One mitigation is to place the telescope as high as possible in a dry climate to get above the heavier, more distorting air. But you can also use adaptive optics. In adaptive optics, a laser creates an artificial star. This system uses a 20-watt yellow-orange laser. The light from that star is measured, and the amount and type of wobble is detected. The computer then instantaneously computes what deformation of the mirror is needed to cancel the wobble, and tiny actuators on the mirror minutely deform it in real time. There are 120 actuators which deform the mirror, each capable of lifting the mirror 2.8 millimeters. The corrected light then continues to the camera sensor. Without adaptive optics, the native resolution is 260 milliarcseconds under ideal conditions. With adaptive optics, the telescope can deliver an incredible resolution of 60 milliarcseconds in visible light. In the near-infrared, Gemini can approach 40 milliarcseconds resolution. The field of view of the telescope is 5 arc minutes, which is about 1/6 of a moon diameter. It's got a focal ratio of f/16. All new large observatories now use Alt-Az mounts because compared to equatorial mounts, they are stronger, lighter, simpler, cheaper, and equally precise. Field rotation issues are handled by derotators on the camera or spectroscope. However, the Alt-Az design means they cannot image targets near the zenith. It took 8 years from breaking first ground to first light in the telescope. Gemini helps us understand the universe's past and future. By observing the light from stars and galaxies billions of years old, it reveals how the cosmos evolved after the Big Bang. Its high-resolution, high-magnification imaging also aids in the search for habitable exoplanets, helping us address the profound question, are we alone? Recent discoveries, like detailed studies of exoplanet atmospheres, bring us closer to answering this question. Gemini enables rapid response observations of transient phenomena like supernova and gravitational wave events. It gives scientists timely, detailed data that no other ground-based telescope can match at that resolution and flexibility. The technology behind Gemini drives innovation in optics, imaging, and data analysis, with applications in fields like medical imaging and telecommunications. Its open access model allows scientists worldwide to use its data, fostering global communication and training the next generation of researchers. We next visited SOAR. This is the Southern Astrophysical Research Telescope. Astronomers still work here as this telescope is not yet operated remotely. It's located just 200 meters away from Gemini South. Soar has a 4.2 meter mirror with adaptive optics, a 1/2 degree field of view about the size of the full moon. Soar mostly takes spectra of astronomical targets rather than photos. It is optimized for seeing into the UV, thus its mirror is coated with aluminum, which reflects UV light better than silver. It's got a real-time limiting magnitude of about +20 and a 300 milliarcsecond resolution when looking at a wide field. In high-resolution, narrow field of view mode, it can approach 30 milliarcseconds with adaptive optics under good conditions. We were able to tour the control room. They operated the telescope so we could see the adaptive optics actuators on the primary mirror, as well as how the primary mirror was protected when not in use. Those of you into astrophotography might recognize the large white area on the wall of the dome. Yes, it's a flats panel, so the telescope can calibrate out dust and transient flaws in the optical train. We saw this later at Vera, Rubin, and other observatories too. We were the first group to see Vera Rubin Observatory since its initial photos were published, and we were allowed unprecedented access to the telescope, control room, engineers, and scientists. Some fast facts about the observatory. It's located on Cerro Pachon Mountain. Its unique shaped building was designed to optimize laminar airflow on the mountain to maximize seeing conditions at the telescope. It has an 8.4 meter mirror. It has an extremely fast focal ratio of f1.2. It's on an Alt-Az mount. It has a world's largest 3.2 gigapixel cryogenically cooled camera. It has an enormous field of view equal to 40 full moons, the largest of any major observatory in the world. It captures 20 terabytes of data every night, and the plan is to image the entire southern sky 825 times over 10 years. In its first image, it captured 10 million galaxies. The telescope is optimized to find transient phenomena like asteroids, comets, near-Earth objects, supernova, etc. We also got access to the main control room for this observatory. Here you can see the operators who choose what to image, for how long, where to point the telescope, how to manage the data, verifying proper operating and safety conditions, weather, etc. An interesting side note, the size of the mirror was limited by the diameter of a tunnel the mirror had to pass through on the way from the coast to the observatory in the Andes. We passed through this tunnel several times. When passing through the tunnel, there was just 10 centimeters of clearance on each side for the mirror. It has a limiting magnitude of +24, a silver coating on the mirror for superior infrared performance, 0.5 arcsecond resolution. The telescope has active optics, not adaptive optics. Adaptive optics, as explained before, work by correcting for rapid atmospheric turbulence over a relatively small patch of sky. But turbulence varies across different lines of sight, and Rubin sees enormous swaths of the sky at once. So correcting across such a wide field at once is not very practical. With active optics, the telescope corrects slow, low-frequency distortions in the mirrors due to gravity, temperature, and mechanical stress. The idea is to maintain the ideal mirror shape over long periods of time. This technique is used because the field of view is so huge. Remember, Rubin's goal is rapid, wide-field images of large parts of the sky. Active optics achieves this. So in summary, adaptive optics are suitable to narrow fields of view. Note that the field of view of the Gemini South telescope is 1,200 times smaller than Vera Rubin. The smaller dome on the hill houses a 1.5 meter telescope that was used to test the camera and provide calibration data. You can sign up to receive alerts from Rubin, as the data is going to be public. Rubin generates about 10 million alerts per night, so you might not want to receive every one. To get filtered alerts sent to your inbox, visit antares.noirlab.edu. Another interesting note is that This is not the Vera Rubin telescope. It is the Simonyi Survey Telescope. Charles Simonyi made the initial large donation to fund the casting of the primary mirror for the telescope. Bill Gates also made a significant early contribution. Rubin is going to scan the sky in unprecedented detail, capturing billions of galaxies and countless transient events over 10 years. Its legacy survey of space and time, the LSST, will help unravel the mystery of dark matter, trace the dynamic structure of the Milky Way, and identify near-Earth asteroids that might one day pose a threat. Rubin's survey is going to transform our understanding of the universe. By cataloging billions of galaxies and stars, Rubin is going to provide a data set so vast it could answer questions we haven't even thought to ask yet. Rubin's data will be publicly available, democratizing science and enabling discoveries by researchers, students, and even citizen scientists. Its advanced computing and AI-driven analysis will benefit industries like data science and cybersecurity. Rubin will also revolutionize our understanding of our own cosmic neighborhood. It will create an unparalleled inventory of asteroids, comets, and other small bodies in our solar system, including potentially hazardous near-Earth objects. This is crucial for planetary defense, helping us identify and track any celestial objects that could pose a threat to the Earth. One of Rubin's primary goals is to shed light on the universe's most enigmatic components, dark matter and dark energy. These mysterious substances make up 95% of the universe but remain invisible and not understood. By meticulously mapping billions of galaxies and observing how their distribution and evolution are affected, Rubin will provide crucial clues to their nature and how they drive the universe's expansion. Understanding these forces is understanding the fundamental fate of our universe. Rubin will be a discovery machine for transients events, supernova, flaring black holes, asteroids, and comets, enabling rapid follow-up observations by other telescopes, including Gemini. CTIO stands for the Cerro Tololo Inter-American Observatory and includes many telescopes over 1 meter in diameter, as well as many smaller telescopes and an automated solar observatory. Cerro Tololo is a nearby mountain to Cerro Pachon. You can easily see observatories on one mountain from the other. Cerro Tololo has a smaller but far higher number of observatories, as we'll see. The first night we arrived, it was partly cloudy. Astronomers were unable to image with the largest telescope on the mountain, and so we got an amazingly in-depth tour of this telescope, the Victor Blanco telescope. The telescope is comparatively old, built in 1976. It's a near twin to the 4-meter Mayall telescope on Kitt Peak. Despite its age, it still operates at peak efficiency and generates over 300 research papers per year. This pace of discovery will be quickly surpassed by the Vera Rubin, but for the last 7 years, this telescope has been the most productive telescope in the world in terms of scientific papers generated. It has a 4-meter aluminum-coated mirror with a plus 26 magnitude limit. The observatory itself is huge compared to a 4-meter telescope built today because it's on an equatorial mount. It used to be classified as a large telescope, but was recently downgraded to a medium telescope due to the higher number of 8-meter plus telescopes now in operation around the world. The U.S. supplied most of the original equipment, and so in order to simplify installation, everything in the observatory runs on 110 volt 60 Hz, which is converted from the local 220 volt 50 Hz supply. Most targets are optical images versus taking spectra, although it does both. The telescope has a relatively new detector. It has an infrared camera for looking at very distant objects. It also has a special dark energy camera of 570 megapixels. This was the world's largest for years. This gives the telescope a 3 square degree field, generating 1 terabyte of data per night, designed for wide-field surveys in the infrared. Recent data they've discovered here suggests that dark matter density is changing over time. This is something else we don't understand yet. The largest comet ever discovered was found with this scope. Comet 2014 UN 271 is about 80 miles in diameter, which is 1,000 times bigger than an average comet. The closest this comet will come to Earth is the orbit of Saturn in 2031, so we don't need to worry about it. We also got a fascinating presentation from an astronomer there about galaxy formation. It's believed galaxies are formed by dwarf galaxies acting as fundamental building blocks. Small galaxies are pulled together to form large galaxies. I was interested to learn that we've discovered that RR Lyra stars are found almost 900,000 light years away from the core of our galaxy. This means the dark matter halo of the Milky Way is about 880,000 light years across. So while the disk of our galaxy is only 100,000 light years across, the halo is almost 900,000 light years across. We also learned that ultra-dwarf galaxies can have as few as 1,000 stars. I asked why this is classified as a galaxy and not a star cluster. The answer? It has dark matter. Open clusters and globular clusters do not. Much of the original data that proved the acceleration of the universe was taken here. The night we were there, they were planning to survey some Type 1a supernova. The next day we visited what they call the Mushroom Farm, a large number of smaller domes with national or university-owned telescopes ranging from 25-inch to 60-inch mirrors. The largest scope in the farm is an 80-inch scope in a separate dome, owned and operated by Brazil. Next, we traveled to San Pedro de Atacama, further up the coast and near to ALMA. ALMA is the Atacama Large Millimeter Submillimeter Array. It's comprised of 3 sites. The main site is the Operations Support Facility, located at 2,900 meters elevation, or about 9,500 feet. The radio telescopes are located up at 5,000 meters, or 16,400 feet, and are called the Array Operations Site, or the AOS. Finally, there are administrative offices for ALMA in Santiago. We visited all 3 sites. The OSF is located at 2,900 meters because Chilean law says 3,000 meters is high altitude, and special requirements would have been necessary, making things much more complex. There are 66 radio telescopes, which can be located in any of 197 sites. Each pad has 2 Ethernet and 4 fiber connections. Each dish features multiple receivers for different wavelengths. They operate at a temperature of between 2.8 and 4 Kelvin. The telescopes are moved with these amazing machines. There are 2 of them. They were custom made in Germany and can lift and move any radio telescope and place it on a new pad in the array, or take it down to the OSF if maintenance is required that can't easily be done up at the AOS. There are 54 12-meter dishes and 12 7-meter dishes. ALMA is a joint operation of the Lab, ESO, and NAOJ of Japan. Water vapor absorbs millimeter and submillimeter radiation, so this site, perched so high in such a dry location, is ideal for this type of radio astronomy. For a long time, this was the highest observatory in the world. Now it's the highest radio observatory. The Tokyo Atacama Observatory is now the highest observatory. It's about 600 meters or 2,000 feet higher. You can easily see it from ALMA on a nearby mountain. One of the challenges is correlating signals from multiple antennas located at different and changing distances from the facility. To do that, they have a rubidium clock accurate to 1 second every 2 million years, and a 16 petaflop computer for the 54 12-meter telescopes, along with an 11 petaflop supercomputer for the 12 7-meter telescopes. This was very fast back in 1998, but it's relatively slow now. The purpose of the computers is to correlate signals from multiple antennas simultaneously with extreme precision. Dishes are very robust and last a long time. Maintenance is more around receiver upgrades, hydraulics, bearings, paint, and lubrication. The telescope is basically a Cassegrain design. It's covered in aluminum. The last antenna was installed in 2015. There were 4 different models, European, US, and 2 different Japanese models. The presence of observatories in Chile has driven the development of communications technology and infrastructure here. High-speed internet benefits citizens, creates construction, engineering, and maintenance work. In high winds, the antennas are put in survival mode. They turn away from the wind and point horizontal. There is a mandatory use of oxygen above 3,000 meters and mandatory daily checkups before ascension to the high site. They look at your blood pressure and your oxygen blood level. Not everyone passes. On our first trip up, 3 of the 10 in our group did not pass the medical check. 9 out of the 10 of us did on the second try. Traveling around to see these observatories, you will notice a lot of trophies. Chile has an annual Inter-Observatory Olympics for employees. All the observatories proudly show off their trophies. ALMA is considered the second toughest operating environment of any observatory. Can you guess number 1? It's the South Pole Telescope. Fun trivia. The South Pole Telescope has an annual around-the-planet 5-kilometer run, and you get a diploma for running around the world. ALMA is working on a major system upgrade. They're upgrading receivers, the supercomputers that correlate signals in real time, and data processing systems. It should allow them to observe 5 times faster, as well as make observations that include significantly more frequencies and in more detail. The new computer will run 10 to the 18th calculations per second. The installation will start in 2028 and be finished by 2030. It will have the effect of adding 6 more radio telescopes due to higher sensitivity. Radio telescopes can be moved, which affects field of view and resolution. There's a 16-kilometer baseline maximum that gives the highest resolution and the smallest field of view. Putting telescopes closer together gives a wider field of view at lower resolution. ALMA will work well with the new ELT, Extremely Large Telescope, which will have a 40-meter wide mirror. This telescope is due to be commissioned in 2030. ALMA has discovered water and complex chemistry in the Large Magellanic Cloud and distant galaxies. It's collaborated with the Event Horizon Telescope to show the first black hole photographs. It's the first telescope to show protoplanetary disks. And ALMA can actually run up to 6 different projects simultaneously. It performs 400 different proposals per year, out of 1,800 which are proposed, and it runs 24 hours a day. ALMA is a great complement to the Very Large Array in New Mexico. As you can see from the diagram, they cover adjacent parts of the radio spectrum. In the ALMA office in Santiago, we saw the control room, and we noticed that there are different color codes given to show the status of each antenna. When we were there, several were offline due to a rare snowstorm that happened just the week before. The colors reflect the status of each radio telescope. You can see things like which are online, offline, being controlled by engineering, might have a receiver issue or maintenance pending, things like that. So what's unique about ALMA compared to other radio telescopes? Well, we have great southern sky access, the highest resolution in the world for telescopes at this wavelength, about 5 milliarcseconds, the most telescopes in any array, and the highest number of countries collaborating. By 2040, 80% of all astronomical observatories are expected to be in Chile. The science conducted at these observatories isn't just about pretty pictures, but about the advancement of science, fundamentally reshaping our understanding of the cosmos, and identifying and tracking asteroids and comets that might threaten the Earth. These are important investments that will reveal the secrets of the cosmos for decades to come. What are some of the benefits of research in astronomy? Remember exploratory surgery? It's almost a thing of the past now that we have advanced diagnostic imaging like CAT scans and MRI. These capabilities were derived from aperture synthesis technology used by radio astronomers. The resulting savings in lost productivity in healthcare is in the trillions of dollars for that one application alone. Imagine a satellite in space taking pictures of the Earth and having to eject a film canister so the pictures could be developed. That's how it used to work. Space exploration and imaging led to the development of digital cameras. The photos you take with your smartphone have roots in astronomy research. GPS would not be possible without an atomic accurate clock, which in turn requires knowledge of pulsar timing. And GPS also needs quasars to calibrate precise knowledge of Earth rotation. Do you have home insurance for a fire or other catastrophic event? Vera Rubin is going to catalog millions of asteroids and near-Earth objects, allowing us to identify any that might pose a risk and have time to deflect them away. Solar observatories help us understand space weather and mitigate the risks of inevitable solar flares and coronal mass ejections, which are pointed at Earth. Satellites and space observatories require lightweight, durable alloys and composite materials. These material science advances have been adopted in aviation and automotive applications. Handling massive amounts of data from telescopes like ALMA, Gemini, and Vera Rubin have led to advancements in data processing and machine learning with applications in finance, healthcare, and cybersecurity. Techniques for studying cosmic rays have led to advancements in precise targeting of tumors in cancer treatments. Astrophysics research into stellar fusion is likely to one day lead to clean, plentiful, ultra-low-cost energy for all. Satellite technology improves communications and entertainment, supports national defense, and enables climate science. Astronomy and space exploration inspire students to choose STEM fields of study, increasing science literacy and workforce skills. Understanding fundamental forces of nature like black holes, dark energy, and dark matter may seem abstract today, but often lead to breakthroughs that can positively impact daily lives. For example, Einstein's relativity was initially dismissed as a fanciful thought experiment, yet now underpins GPS and nuclear energy. And while quantum mechanics may seem completely abstract, it helps explain fusion and many astronomical principles and has led directly to the transistor, integrated circuits, and then computers. The U.S. spends just 0.09%, less than 0.1% of the 2024 budget on astronomy-related research. We get an incredibly good return for our investment. Thanks for watching. Please hit the subscribe button as it helps me with the algorithm.